Hello everybody and welcome back to the channel. As you can see, my Jufro is in full effect today and I refuse to get a haircut, so it's probably going to stay like this for a hot second. This is a pretty important recording for me today, and I've actually put on some underwear in order to celebrate, which is a huge accomplishment for me because I don't like getting up from my desk very often. Anyways, today let's talk about Shazam. This is one of those services or problems that if an interviewer asks you this, they're probably smoking crack. But at the same time, it's genuinely an interesting distributed systems problem, and I feel like there's still things we can talk about in addition to the core algorithm that are actually exemplary of stuff that you could be quizzed on. And so yeah, I think it's still useful overall, but if you're just here to learn a little bit, that's what I did as well, and it's pretty interesting, so let's get into it. Okay, so the functional requirements of our service are pretty simple. Basically, all we're going to be doing is building some sort of music recognition service, which means that we're going to allow a user to take in an audio clip into something like their phone microphone, and then, they'll send that to our servers, and afterwards we're going to return them a suggestion of what we think the song that they just heard is. As far as capacity estimates go, this is going to be a little bit backwards. The reasoning for that being that I'm kind of going to mention a key term here that we'll cover in a bit, but it'll make sense a little bit more later. Basically, I'm going to assume that there are 100 million songs that we're having under consideration. And then basically per song, let's imagine that there are 3,000 indexable keys. And I'll touch upon this later. What I really mean is something known as fingerprints, but again, we'll speak about that later. And if each of those indexable keys is 64 bits, then we can basically say that we're going to have to create an index that is 2.4 terabytes. So obviously that's going to be pretty big. We can't fit it all on one machine, or I guess we could with a hard drive, but if we plan on doing any sort of processing in memory, we're going to have to be doing sharding. And in addition, 2.4 terabytes is a lot anyway. You would probably want to do some sharding regardless, because that obviously has an ability to grow. The API for this service is pretty quick. It's just going to be that we can go ahead and find a song, and the one parameter that would take in is the recording of a song. So let's go ahead and get on into the database design. Well, if you think about this problem as kind of a search problem for databases, then there's really just going to be two things that you would need. The first one is going to be some sort of index that allows us to take in our client-side clip of audio and spits out some potential IDs of audio that, we could be playing. And then the second thing is probably going to be some overarching database of all the audio files or something pertaining to the audio that we can go ahead and search afterwards and return back to our user. Okay, so let's talk about an algorithm for a music recognition service like Shazam. Like I said earlier, it's completely absurd for any sort of interviewer to ever expect you to know something like this because, it's quite literally a multi-$100 million idea that they would be expecting you to just come up with on the spot. But I think it would be somewhat reasonable if they kind of gave you a bunch of hints about what was going on and then said, well, now that we have this algorithm, how would we actually kind of support this in a distributed environment? So anyways, let's go ahead and get into it. We know that our entire goal is basically to take a sample of audio data and convert it to a format where we can just go ahead and match that with, existing audio data that we have in our databases. And of course, this needs to be done with a service that is both highly available and also has very low latency. That's going to be a requirement in any sort of systems design interview. So anyways, before we can really start getting into the algorithm, we have to talk about just how audio files work in general. Audio can be represented by something known as a spectrogram, which is a 3D graph, and I'll put one of these up on screen so you guys can follow along. A spectrogram basically has three parameters. It has the time that you heard a specific part of the audio, it has the frequency of the wavelength of the audio, and then additionally it has the amplitude, which kind of represents something like the volume. So Shazam does kind of a clever optimization, and this is something that they've actually written in their paper. I'm just not making this up on the spot. But basically, they take all of the peaks at certain amplitudes within the graph, in this 3D graph, and they reduce this 3D graph down to a 2D graph and create something they call a constellation map, where basically now we have a 2D scatter plot of all these points that were at really high amplitude, and basically now they're just, little scatters on basically a plot of both the time and frequency. So this allows us to simplify our search space pretty considerably, and it also allows us to account for variations between things like the actual audio clip that we might have in our database and also the audio clip that a user might play for us. Obviously, there's going to be a lot of variation that can happen between the two of those, between things like, device compression, external noise, and just a bunch of other factors. And as a result of that, kind of reducing this complicated 3D graph down to this more simple 2D one allows us to have a better chance to be able to match these songs together. So now that we have these 2D graphs, what can we actually do in order to kind of start dealing with creating a song index and making it such that we can search songs quickly? Well, this is where something known as a combinatorial hash comes in, and Shazam goes ahead and does something like the following. One option would be that every single point on that constellation graph, we could go through all of those frequencies at a given time, and we could say, well, what songs have all of these, frequency points at a given time? But there's a couple issues with that. The first is that, well, frequencies are basically representing like the note of the song that you might hear. So if you're just looking at one frequency and trying to, limit down your fields of songs based on which songs have that frequency, most songs are probably going to have it. It's like saying, what songs don't have like the note C when you're looking at all of music. They probably all do. So what Shazam does instead to limit down the space is they actually look at pairs of notes. And this has a bunch of really useful properties. So basically, if you take two frequencies, so two of those points on the graph, and you take the first one, which comes before the second one in time, and you say the first one is what we'll call the anchor point, basically create some sort of tuple where we have, the anchor frequency, the second frequency, and then the last thing is going to be the amount of time and offset between them. Now, this is really useful because, one issue with having to create an index like this is we don't know where the user's clip is going to be played in terms of at what point in the song it starts, right? My song could be 3 minutes long, but I might be playing an audio clip from my phone where it starts a minute in. So we have to be able to align all of these clips. So actually using pairs of these frequencies with the time delta between them is super useful, because if we can find basically, for our user audio, if we split it into a bunch of different pairs of points where we have the anchor point and then the second point and the time between them. Let's say we have, like I estimated earlier, 3,000 indexable keys per song, where the key is going to be one of those tuples. Then all we have to do is basically figure out the song in the database where we have the most alignments between the user clip and that song. And we can get, genuinely a lot of alignment because, like I said, we kind of reduce this complicated 3D graph with a lot of potential for noise into a more simple 2D graph, which, gets rid of a lot of the variation that can occur from having to use client-side audio through a microphone. So basically now here's what's going to happen. For our, let's say, 30-second user clip of audio, we're going to create a bunch of all of these, anchor point, secondary point, time delta tuples between them. It could be up to something like 1,000. And in theory, we can really get a lot of these hashes. And the hash is basically going to be comprised of that tuple. Let's say, we want a 32-bit hash. We can basically use something like 10 bits for the first frequency, 10 bits for the second frequency, and then 12 bits for the time delta between them. And so now, for our given user clip, we have all of these different hashes that we can look up in the actual index. And we're going to do that. So if we have an inverted index where basically the inverted index also is taking all of these hashes or these fingerprints of all of the existing songs that we know, and says, for this hash right here, here are all the song IDs that correspond to it or have that exact hash, then we can look up all of the hashes in our user clip, find all of the potential songs that we have to, look at to compare them, and then say, okay, now we have all these potential songs where one hash is matching. what is the best match we can get when we look at all of the hashes in our user clip. So basically, it's a two-step process. We use all of the hashes individually in this kind of index search where we get a bunch of possible song IDs, and then we limit down all of the potential song IDs to just one by comparing all of our hashes in our user clip of audio and seeing how well they line up with some basically sequence of hashes within all the candidate songs. And so that's basically the algorithm right there. It's not overly complicated, but the reason that I kind of like this problem is because now once we have this idea of, okay, first we're hitting this, big inverted index, and then after that we have to pull a bunch of things from a database and do a bunch of processing in order to kind of, figure out which song matches best. There's a lot of CPU work to do there, and it's not easy to speed up. So how can we actually go ahead and do that? Well, for starters, as I mentioned earlier in our capacity estimates section, our index is probably going to be in the order of magnitude of terabytes. In fact, I estimated 2 terabytes. And so if we really wanted to basically have super fast, matching, in an ideal world, we'd be able to use something like memory with a hash map, where the hash map is the key, which is going to be that tuple, that 32-bit thing I mentioned earlier, and then the value is going to be a list of song IDs that are held in the database. But in commodity servers these days, it's rare that you can have more than 256 gigabytes of RAM, and as a result of that, we're going to have to be able to shard our index in order to really get everything in memory. We could put things on disk, but then we're limiting ourselves to pretty slow performance because we're basically going to have to perform a binary search for all of the, corresponding hashes. We've spoken about this in the past. You're really basically limited to logarithmic time complexity when using a disk-based solution, whereas with memory, not only are you getting faster accesses just because it's in memory, but you also have a hash table, and that allows you to get constant time accesses. So that's probably the ideal way of storing this index. That being said, we have to come up with a good way of actually sharding out our index. One nice property of the actual hashes that have been created is that 32-bit key is going to start with some encoding of the anchor point. And so since we're going to have a bunch of hashes with the same anchor point, it's going to allow us to send basically a bunch of requests for one anchor point, but then a bunch of different secondary points all to the same search index node, which is really useful because consistent hashing will basically make sure that all of those keys with the same anchor point are probably going to be on the same node. And then in addition to that, we're probably going to have to parallelize the rest of our requests because they may have a different anchor point in that tuple. And I'll make sure to kind of draw this out so it makes sense for how we're actually looking to get all of those hashes. So either way, one way or another, we're probably going to have to be making a bunch of different calls to different shards of that index. And in an ideal world, because they're parallelized, it'll all be decently fast and returned back to our server quickly enough. But even once we do that, even if we're able to achieve low latency just in that index alone, we still now have to do this entire secondary phase of processing where we check out all the possible songs and calculate which one is the actual best match. So now again, we could basically come up with another problem where that has to be fast, but basically the only way I can think about how you would do it is either you keep all of those songs in memory, which would be really useful because in theory keeping all of the fingerprints for every single song should be the same exact size as the inverted index. It's just stored in a different format, so you could shard it as well and still use memory again. Or perhaps, and this might be a little bit more practical, is for the popular songs, at a given time a lot of people are going to be wanting to figure out what one particular song is. You can actually just go ahead and cache the sequence of fingerprints for that song, and as a result, it should greatly speed up a lot of those operations and requests to the database. But either way, no matter what happens, because you're going to have multiple terabytes of data to store in terms of songs, you're going to have to parallelize these computations, and in fact you should, because all of those songs are separate entities, and as a result you can perform the computation of similarity between the user audio clip and a given song audio clip separately. So it should be totally fine if you're making a bunch of parallel different requests to different shards of the database, and then on some sort of aggregation server you would go ahead and basically say, okay, which one of these songs match the closest to our user uploaded clip. Then the final piece of the puzzle is probably just going to be that every once in a while there are going to be new songs that are created and uploaded and recorded, and as a result of that we're going to need some reoccurring batch job that's going to take in those new songs, get the fingerprints for them according to the algorithm that I mentioned earlier, place them in our index, and also place them in our database itself. Okay, so as always, let's formalize all of that with a diagram. So basically imagine we have a client who wants to figure out what it is that they're currently listening to over the radio. And the first thing they're going to do after recording that clip on their phone is hit a load balancer and upload that clip to the recognition service. The recognition service is then basically going to go ahead and say, okay, I know now that I basically have all of these fingerprints for the user uploaded clip. Let's look them all up at the same time in parallel in our fingerprint index, which in an ideal world we can keep in a memory-based database solution such as Redis. Once it basically gets all those lists of potential song IDs, the next thing it has to do is reach out to the matching service with that aggregated list. And then the matching service can basically say, okay, I have all these song IDs which I need to get the fingerprints of. If they're in the fingerprint cache, then great, that's going to speed up some of the requests. If not, I have to fetch them from the database. You'll see that I used a MongoDB database for the songs here, and there are a couple reasons for that. The first thing is that it still uses a B tree, even though it's NoSQL, which is nice because B trees in theory at least should be faster for reads than an LSM tree. Additionally, another nice thing about the MongoDB is that because it is a document store, you should have really nice data locality, which should allow you to fetch basically the huge document that is going to be, one song ID and all of the corresponding fingerprints for that. So those documents can get pretty big, but as a result of that data locality, hopefully the reads will be a little bit faster. And then the final component of the puzzle is basically just having some sort of Hadoop cluster, which as new songs are created and published, will go ahead and use a daily Spark job to go ahead and update both the index and the database to account for all of the new songs. God damn. As you can see, I'm already fucking starting to sweat, which is unfucking believable, but yeah, turn my air conditioner off for like 5 minutes, and this is what happens in this new place. So I guess every time I record, I'm just gonna be a sweaty motherfucker, but is what it is. So anyways, guys, I hope you enjoy this one. It's an interesting problem. Like I said, I wouldn't expect that anyone would ever ask you this, but I don't think it's unfair if someone gave you, like, I don't know, a 10-minute primer on how those keys are created for a specific song, and additionally, kind of the process of how you would figure out once you have the fingerprints of the user clip and also the fingerprints of the potential candidate songs, and then basically say how would you distribute this. That's decently fair, but I just can't see it happening. I've just heard of this problem as a systems design problem, and I like to cover it. It's what I do. Hit them all. Dirty little dude. So yeah.